Okay. So, good evening, learners. Please try to join the class, the live interaction session itself. The recordings are only for the students who are not available on this time slot, because in the live interaction session, you can also solve your doubts, or you can ask your doubts, and you can be with the pace of the course. So, welcome everyone to the NPTEL course on post-harvest operations and processing of fruits, vegetables, spices, and plantation crop products. So this course is instructed by Professor H.M. Mishra sir, who is a professor in the Department of Agriculture and Food Engineering. And he is the faculty in IIT Kharagpur. My name is Shikha Sharma. I am a research scholar in the Department of Chemical Engineering, IIT Guwahati, and I am the teaching assistant of this course for July 2026 semester. And today we are going with our week 3 live interaction session. So it will going to help you to solve your assignments for the respective week for this week 3, and the assignment deadline for week 3 is 12/8/2026. So please submit your assignment on time. So the topics that we will be discussing in today's class will be module 3 basically, which includes lecture 11 to 15, which basically includes the lectures regarding the basic principles of processing and preservation. So it will include the basic principles of processing and preservation of basically the horticulture products or the plantation crop products. And lecture 12 includes basically the processing by removal of water. And lecture 13 is about processing by the addition of heat. And lecture 14 is about processing by removal of heat. And lecture 15 is about irradiation of fruits, vegetables, and spices. So basically these 5 lectures, basically they are uh, the they are covering all the aspects of the processing and preservation of the horticulture products or the plantation crop products. So I hope you have gone through these 5 lecture videos already. So if you have any doubts regarding these 5 lecture videos, please feel free to ask. And also if you have any doubt regarding week 1, week 2, or the module 1, module 2 lectures also, you can ask your doubt. So, okay, let's begin with our session, which will basically be covering some of the concepts regarding these 5 lecture videos, and also it will cover some of the numerical questions as well. So let's begin with today's session. So basically, let's discuss the basics first. So basically, the microorganisms, they are like, if the microorganism is there, its parent cell is there. So what basically is going to be there? So it will divide, like it will grow by dividing itself, like the cell division will happen, and then 2 daughter cells will produce from it. So that is a process of reproduction is binary fission. So it will follow binary fission to multiply. So it will be from one parent cell, 2 daughter cells will produce. From 2 daughter cells, 4 will produce. So like this, there is an exponential growth in the like in the growth of the microorganism. So when the microorganism is inside the food, so what are the different factors which will going to affect the microbial growth will be the intrinsic factors, processing factors, extrinsic factors, implicit factors, and the net effects, and their net effects also. Okay. So what are these different factors which are affecting the growth of the microorganisms? So intrinsic factors includes basically the chemical and the physical parameters within the food from which contaminating microorganisms is therefore inextricable in contact. So basically what is there, this intrinsic factors are basically the factors which are there inside the food, like the composition of the food, the pH of the food, or the water activity of the food. So these are the intrinsic factor because it is uh, inside the food and it will be in direct contact with the microorganisms. So it is food and it is microorganisms. So it is directly in contact with this microorganisms. So it is going to directly affect the growth of the microorganisms. Then processing factors. So that is includes the factors which are basically applied during the processing of the food. When the food is being processed, that time what are the different factors? Uh, they are the processing factors. They will also affect the growth of the microorganisms. So if we have some different kind of processing method and it will inhibit the growth of microorganisms, so that will going to enhance the shelf life of the food. Then extrinsic factors are also there. So extrinsic factors includes that is the factors that influence microorganisms in the food, but which are applied from the outside the food and act during the storage. So there are the different extrinsic factors, like the factors which are from the environment and contributing or affecting the growth of the microorganisms. Then implicit factors are also there. So this includes basically this includes factors that are related to the nature of the microorganisms themselves and to the interactions between them and with the environment, which with which they are in the contact during the growth. So implicit factors are the one basically which are related to the nature of the microorganisms themselves and also to the interaction between them and with the environment. So these are the factors which are the implicit factors, and the net effects are the overall effects of all these. So this takes into account the facts that many of the factors strongly influence the effect of each other on microorganism growth and its survival. So the overall effect of combinations of factors may not be readily predictable, but may be useful greater than the perceived effects of the single factor. So basically, we have the different factors as well. Uh, so they will all the intrinsic factors, the processing factors, the implicit factors, the extrinsic factors. So there are different factors. These so their net effect. So some one factor like one factor will not going to like the pH alone cannot able to sometimes hamper the growth of the microorganism. So we take many factors together, like RH also, we will control RH also, we control the temperature of the food also, and then we're gonna control other factors as well. So their net effects will going to give the food, which is the fresh like food, fresh like fruits or vegetables or any food products. So we'll get fresh like food product, and the microorganisms will also be, the count will be low, or there will be no pathogens in the food product. So it will not be contaminated food product. So we take many factors into the account, like there is a concept also which is known as a hurdle technology, which we'll be discussing in the further classes. So hurdle technology works on the same thing, that because if we are applying heat, so we have to apply one hurdle with the greater intensity, and it may deteriorate the food quality. So what we're going to do, we'll apply several hurdles, so that to be in the uh, like the optimal quantity, so that the quality of the food will also not hamper, and these all hurdles will play the role together, and they will going to give some synergetic effect, and then microorganism growth will be hampered. Okay, so let's discuss our first question. Which of the following statements are correct regarding the factors influencing microbial ecology in the foods? So what are the different factors which are influencing the microbial ecology in the foods are? So we need to tell which statement is correct. So one is extrinsic factors, which includes the temperature and the oxygen tension. So it will be on during the storage. And then second is water activity, or the ERH, which is equilibrium relative humidity, is considered as a chemical intrinsic factor. Then third is food composition and microstructure are intrinsic processing factors. And then the fourth one is fourth statement is antimicrobial substances and the redox potential fall under the implicit factors. So we need to tell which statement is correct here. Okay, let's discuss the solution part. The solution is saying that 1 and 3 options are only correct. That means the extrinsic factors include the temperature and the oxygen tension during storage, and third is changes in food composition and microstructure are intrinsic food processing factors, or the processing factors. So these are the correct. Let's see uh, the reason behind it. So basically, we are talking about, in first case, about temperature and oxygen as a extrinsic factor. So yes, obviously, in extrinsic factor, we have ERH during the storage, then we have temperature, and also the oxygen tension, which is in the extrinsic factors. So it is correct. Then second statement is about water activity. So water activity, we can find here that the equilibrium relative humidity and the water activity is in the physical factors, right? And it is also comes in sometimes the extrinsic factors. So it is basically because ERH is basically the environment relative humidity. It will not come under the intrinsic factor. So if we will talk about the specifically the what is the water activity of the food product here, because we are talking about water activity of the food product and water equilibrium relative humidity in regards to the food product. So it will come with the, not with the environment. If we are talking about environment, then it will be in extrinsic factors, but we are here talking about the water activity or the equilibrium relative humidity of the food product. So it will come in the intrinsic factors, but in the physical parameters. It is not a chemical parameter. So it is not a chemical parameter. Then the food composition and microstructure. So it will come under intrinsic and processing factors. So changes in the food composition, changes in the microbial type, changes in the microbial number, and microstructure of the food. So it comes basically in the intrinsic processing factors. And the antimicrobial substances and the redox potential, it will be the chemical intrinsic factors, and it is not in the implicit factors. So in intrinsic factors, in the chemical one, so nutrition is there, then pH and buffering capacity, then oxidation reduction potential, and then antimicrobial substances are there. In implicit factors, what are the different factors will come? So the microbial growth rate, and then the synergetic effects and the antagonist effects, they come in implicit factors. So here answer 1 and 3 is only correct, are only correct. 2 and 4 statements are incorrect. Let's discuss about these all intrinsic and extrinsic parameter in a bit detail. So first we are talking about temperature. So temperature is basically because of the temperature, like in the food, we have microorganisms, right? So the temperature of this food will affect that which type of microorganisms can grow inside this particular food. So if the temperature is around like this, which is the optimal temperature, but it can grow in this, like in the growth range, it can, these are the classifications of the organisms. So psychotrophs, they are the organisms which can grow from 0 to 20 degrees Celsius, but the optimal growth can be seen from 14 to 20 degrees Celsius. Then there are mesophiles, thermophiles. So mesophiles, they can grow in the optimal temperature of 30 to 37 degrees Celsius, and thermophiles, as the name suggests, that they are the heat tolerating microorganisms. So they can grow up to from 50 to 66 degrees Celsius. So based on the microorganism in which growth temperature they can grow. So there are different classifications, like um, from 0 to 20 psychrophiles. Mesophiles are the one from maybe 15 to 45 around, and in between, like from 10 to 30, these are the psychotrophs. Then thermophiles are the one from 40 to 70. Then extreme thermophiles are the one from 65 to 100 degrees Celsius or 105 degrees Celsius they can tolerate. Then there are based on the oxygen stress. So the microorganisms can be classified as these different 5 classifications. So the obligate aerobes are the one which needs oxygen to grow. So that's why they'll grow at the surface, because they'll get oxygen from here. And then the obligate anaerobes are there, which are the one which cannot tolerate oxygen. So they will grow at the bottom, so that the oxygen contact will be minimal or zero. Then facultative anaerobes. So they will basically take both the oxygen, they can like grow both in the oxygen and without the oxygen environment. Basically, they are the anaerobes, so they will not grow in the oxygen, but they are the facultative ones, so they can tolerate the oxygen as well. Then aerotolerant anaerobes. So aerotolerant anaerobes are the one. So facultative anaerobes are the one which can take more, like which can survive with the more oxygen. So if there are they are the one which can grow in the oxygen atmosphere well, and they are basically the anaerobes. But in the aerotolerant anaerobes, they are the one they can tolerate the oxygen. So they will be growing in the whole media. They can tolerate, means they don't want oxygen, but if the oxygen will be provided, they will tolerate that. And then micro aerophiles are the one which needs little amount of oxygen to grow. So they'll grow in little below the surface, so that they can get less amount of the oxygen. Then the water activity, basically, so the water activity is basically the inherent property of the food product. So it is a ratio between the vapor pressure of the food itself when in a completely undisturbed balance with the surrounding air media, and the vapor pressure of distilled water under identical conditions. So this is the water activity, AW is equals to P by P naught. So if we multiply this water activity with 100, we will gonna get equilibrium relative humidity, ERH. And the water activity, basically it increases with the temperature. Most food have a water activity around greater than 0.95. So they will provide sufficient moisture to support the growth of the bacteria, yeast, and the mold. So we can see that the water activity, if it's great, from 0.7 to 0.88 moles can grow, from 0.88 to 0.91 yeast can grow, and from 0.91 to 1 very high water activity, then bacteria. can easily grow in such environment. Then next factor is the composition of the food, or the uh, like the different nutrients which is there in the food. So uh, basically, microorganisms need sufficient amount of the nutrients so that they can grow. So which kind of nutrients microorganisms need? So they need some kind of energy sources like carbohydrates, amino acids, proteins, organic acids, and the alcohols. And then they need a nitrogen source such as the amino acids, peptides, nucleotides, urea, protein, and ammonia. Then they also need some kind of carbon sources and minerals like phosphorus, then iron, and then magnesium or manganese, and then they need calcium, also the potassium. So they also need the vitamins and other growth factors as well, so that they can grow. So if the food is rich in these kind of nutrients, so microorganism can easily grow in that. So if the food is rich in the protein or proteinaceous food is there, then microorganisms can spoil and the putrefaction can occur. And then if the micro food is carbohydrate rich, so fermentative spoilage will be more. So some and the growth of the microorganism will depend on the limiting factors. So if some nutrient is in the limiting amount, that will going to limit the growth of the microorganism. Like vitamins in the fruits, low vitamin B content is there. So most of the molds, yeasts, as a spoilage microorganisms, they can synthesize them. So basically, they can also some of the yeast mold can synthesize vitamin B more and can grow in that kind of food where the low amount vitamin B is there. Then the microstructure of the food or the biological structure of the food is also going to affect the growth of the microorganisms. Like in some food, there are natural barriers, like in the egg, there is a shell, which is the natural barrier. And in the fruits and vegetables, cell wall is there, and in fish, skin is there. So these kind of the natural barriers, and the oxidative and the reduction potential will also gonna impact the growth of the microorganism, because like we can see, if the microorganism, if the EH, which is the oxidative reduction potential, so if it's high or positive, so aerobes can grow, like which needs oxygen, microorganisms like which need oxygen. And if low EH or negative EH is there, then oxygen is toxic for them and anaerobes can only grow. At high and low EH, so the facultative anaerobes can grow, and relative low EH values, microaerophiles can grow. So what is this oxidation reduction potential? So it is basically the ratio of the total oxidizing power, so which is electron accepting power, to the total reducing power of a substance, which is electron donating power. So it is basically the ratio of electron accepting power to the electron donating power. Like like if we are talking about this Cu, so this substance is, it is taking oxygen. Basically, it is undergoing oxidation by taking the electron, and if it's releasing the electron, it is undergoing the reduction. So this way, the oxidation reduction potential is there. So this is basically measured with the ease by which a substance gains or loses its electron. So it is basically measured in multivolts, millivolts, milli-MV, which is milliwatt. So the more oxidized substances will have high EH, and more reduced substances will have low EH. So this negative EH means that the substance is having more of the reduction potential, and anaerobes can grow in that particular environment, whereas the aerobes can grow in more like uh, positive EH, which means they have the oxidized, the more oxidized substances are there. Then in some food products, antimicrobial agents are also present. So based on that, if the different antimicrobial agents are there, so microorganisms will gonna die if certain kind of microorganisms can die. So the natural constituents of the food which affects microbial growth are like lysozyme. So it is present in the egg. So it attacks bacterial cell wall. And then lactoferrin in the milk. So it chelates Fe. Then lactoperoxidase, it's present in the cow milk. So it is an antibacterial and oxidative stress giving to the microorganism. Then glutenin, so it is also there in cow's milk. Then coumarins, so it's present in the fruits and vegetables. Then allicin in garlic and onion, and polyphenols in the green and the black teas. Then essential oils are there in some spices and the vegetables like eugenol, cinnamic aldehyde, then allyl isothiocyanate, then thymol, then carvostol. So these kind of essential oils are there. And then some kind of preservatives like the benzoic acids, lysine, and the sorbic acids. They are also present in some kind of foods and some kind of food stuffs, and they can act as an antimicrobial agents. So these basically are all the factors based on that microorganisms growth will be there, or the growth will be inhibited. Okay, let's move to the next question. That traditionally used, the assertion is saying that traditionally used food preservation techniques aim to slow down, inhibit, or kill microorganisms or restrict their access to the food. Reason is saying that these methods create unfavorable condition for the microorganism to grow by altering the intrinsic and extrinsic factors like the temperature, water activity, oxygen availability. So we need to tell if the reason, assertion and reason are correct, and if a reason is giving the correct explanation of the assertion. Okay, let's see the answer. So basically here both assertion and reason are correct, and the reason is the correct explanation of assertion. So we have this preservation, these traditional food preservation techniques, and it has worked with the three aims like slowing down, or in some instances complete inhibition of the microbial growth. And then second is direct inactivation or killing of the target bacteria, yeasts, and molds. And third is restricting the access of the microorganisms to the food products. So assertion is correct. So this first parameter, which is first way or aim or first method to is the slowing down or inhibiting the growth of the microorganism for preserving the food product. So in this, how we can slow down or inhibit the growth of microorganism by lowering the temperature like chilling or freezing, or alcoholic fermentation like brewing, or we are fortifying or vinification. And then we are reducing, third way is reducing the water activity or raising the osmolality. Then it is done by drying, basically curing and salting, and then conserving with adding of the salt sugars. So we can add salt or sugar, or we can dry so that the water activity can be altered of the food product. Then acidification methods like mm, adding the some kind of acids from outside, or adding some kind of the microorganisms, or doing the fermentation so that the acids can reduce. Then chemical preservatives can also be used, like sulfides, nitrites. So some kind of organic compounds like the sodium sorbate or the sodium benzoate, parabens or calcium propionates, they can be add as a chemical preservatives. Sometimes the antibiotics like the niacin, they can be added to the food product so that the growth of the microorganisms can be inhibited by the chemical method. Uh, Using the chemical, then oxygen can be decreased, like reducing an inert atmosphere or the vacuum environment. Then CO2 concentration can be, or O2 CO2 concentration ratio, they can be altered in the, like in the case of the controlled atmosphere storage or the modified atmosphere packaging. Then nutrition amount can be restricted, like in the emulsions, water in oil emulsion. So if the nutrient amount can be reduced, so the growth of the microorganism will be slow. Then from direct inactivation of the microorganisms, like from the heating, pasteurization and sterilization, or irradiation method like radiation and radicalization or adaptation. And then the microorganism access can be restricted to the food using the decontamination methods, like by the ethylene oxide treatment, or by including the packaging material, and also by including the packaging material and also treating the packaging material. And then from the aseptic processing, so aseptic thermal processing and packaging can be done so that we can get the contamination of the microorganisms can be restricted. So here in this question, as we discussed, that the assertion is true because all these three traditional preservation strategies are correct, and also the reason explained correctly the assertion that the preservation techniques, they basically are working based on altering the intrinsic and extrinsic parameters like the temperature, water activity, oxygen availability, so that the unfavorable environment for the growth of the microorganisms can be created and microorganisms can die. So here A is correct, that the assertion and the reason both are true, and reason is a correct explanation of assertion. So basically these are so microorganisms, they can be basically killed, or the food can be preserved using different methods. So the fruits and vegetables, they can be preserved using different methods, like removal of the water or the moisture, then application of the heat, lowering of the temperature, and control oxygen, and pH reduction. So in the next question here, we are discussing the how we can this pH will going to play a role in the growth of the microorganisms. So this question is about so a food technologist is basically trying to develop a product with extended shelf life by controlling microbial growth. So which of the following strategy can help control microbial growth in the food product? So first is choosing plants or animal raw materials with naturally lower or higher pH. Then second statement is adding low molecular weight acidic or alkaline compounds to adjust the pH. And then third is maintaining a neutral pH to minimize the growth of the or the activity of the microorganisms. And fourth is that utilization of both the high and the low pH extremes to inhibit microbial growth. Okay, let's see the solution. So here statement 1, 2, and 4 are correct basically. So let's talk about the pH. So this pH is basically an intrinsic parameter of the food product. So it is going to affect the growth of the microorganisms and also the sensory properties in the food products. So this is basically the pH meter. Here we put our solution and this is a pH probe which is going to measure the pH and the readings are reflected here. And then basically pH is the actually pH is dependent on the H plus, which is hydrogen ion concentration. So pH is equals to minus log H plus ion concentration, and POH is minus log OH minus ion concentration. So pH plus POH is gonna equals to 14. So this is the basically the constant in Canning calculation. We take that the concentration because H2O is basically converted into H plus and OH minus. So based on that, we are saying that the total will be equals to 14 if we are saying pH plus POH. Okay, so let's discuss our question. Back to the question. So a food technologist is basically trying to develop a food product with extended shelf life by controlling the microorganism growth. So how the control of the microorganism growth be possible? So based on the pH, how we can control the growth of the microorganism. So basically pH, this pH, so pH affects basically microorganism or microbial energy metabolism because it involves, so pH affects basically microbial energy metabolism because uh, when the pH is altered, so microorganisms need some kind of energy so that it will trying to adjust with the or with the changed pH concentration. So pH basically affects microbial energy metabolism involving the buildup of gradient of H plus across the membrane. So suppose this is a microorganism and based on the H plus ion concentration outside, so microorganisms need to maintain a stable condition. So some energy of microorganism will be consumed in this process. And microbial enzyme activity and thus microbial enzymes activity, it will also gonna impact yeah, or it will also dependent on the pH outside. And also the stability of the cellular macromolecules like the protein structure and like these, they are dependent on the pH. So overall, this pH is influencing the growth of the microorganism. So pH can be controlled basically by choosing appropriate raw material in the food product like a specific plant variety or animal tissues, and by adding or in situ formation of acid or alkaline low molecular weight compound. So either we can maintain the pH of the food product by making the food product with certain low pH substances, or sometimes we can basically add some products, or sometimes like due to fermentation or any other process, some kind of low molecular weight acidic or alkaline substances can produce. So pH at the so at the low or very high, that means acidic or alkaline. So both the extremities are not feasible for the growth of the microorganisms. So both low and high pH basically can inhibit the growth of the microorganism. Only microorganisms typically grow in the neutral pH. The minimum pH for the growth and the rate of inactivation by acid is indeed affected by the nature of the acidulant, the presence of other inhibitory factors like the low water activity, preservatives, low temperature that may interfere with the energy metabolism or increase the need for maintenance energy, and the ability of the microorganisms to react to acid stress and to maintain passive and active pH homeostasis. So the microorganism growth is dependent basically uh, on the pH as we discussed. But how much pH should we maintain in so that the microorganism growth will be inhibited. So basically, it depends on the which kind of like acid we are adding on in the food product. So its nature will gonna depend, and the other inhibitory factors or the other hurdle factors will also going to tell if other hurdles are there. So microorganism energy can be taken up by other hurdles as well. So with the even with the mm, mm, like low changing of the pH, or maybe at 5 pH also we can gonna, which is near to neutral. So we can going to get the microorganism kill, because other hurdles are there which is going to take up the energy of the microorganisms. So it, and also the nature of acids depend, because also the nature of microorganisms also are important, because some microorganisms can tolerate high pH change, whereas other pH cannot maintain that homeostasis. So passive, so what are this passive and active pH homeostasis? So passive pH homeostasis means that the microorganisms either prevent external protons from the entering inside the cell, or increasing the buffering capacity of the cytoplasm by synthesis of the glutamate or other citrates. So this hemostasis is very important in any microorganism, because hemostasis is the tendency to maintain the uniformity and stability in the internal microbial cells, which is essential for its survival. So in microorganism, there is a stable kind of atmosphere should be there. So to when the pH is going to change, so its hemostasis will going to influence. So to maintain the hemostasis, microorganism will try to resist the change. So how it will resist the change? So by the passive and active method. So the passive pH homeostasis can be eh, can be maintained when the external protons can be the external protons will be inhibited by the cell wall, or some kind of buffering agents will be produced from inside of the cell, which will if it is producing certain kind of some buffering agents, so the cell, microbial cell will, the energy of it will be gonna exhaust. And the active pH hemostasis is basically that the cell maintains their cytoplasm pH through metabolic activity. So if the cytoplasm of the cell will going to be maintained or changed based on the outside environment, so that is the active pH homeostasis. So here we can see that there are different food products which are in the different pH ranges. So the ammonia is basically in the alkaline side, whereas the milk is in the more neutral side, and the apple and the lemon are more towards the acidic side. So till the pH homeostasis is maintained inside the cell, the microorganism will gonna survive. So the microorganism, it will going to try to maintain the pH either by active, passive, or active pH homeostasis. So microbes try to manage and try to fight with the stress, and this way it will going to exhaust all its energy. So if we apply several hurdles, so all the energy will be exhausted in the microbial cell, and then it will going to die. Like the composition of the food, which is apple, it is its pH is less than 4, around 3.3 to 3.9 because of the malic acid, and in the tomato, the pH is around 4.3 to 4.9 due to oxalic acid, and pH milk is slightly towards neutral. Yeah, so the pH of the milk is slightly towards the neutral, which is around 6 point, sorry, so it is slightly towards neutral because of the lactic acid. So its pH of the milk is around 6.7 to 6.9. So here in this table, we can see different vegetables and different fruits and their pH. And here it is telling that which kind of microorganisms can grow in different pH. So if the pH is very low, in very low to very high pH, it's a very wide range, molds can grow. Then yeast and then Alicyclobacillus species, and most of the bacteria they are like in the they are growing mostly above to 4 to 9. So they are neutral pH. So here we can see that choosing plant or animal raw materials with naturally lower or higher pH will gonna work for us. So it is correct. Then adding low molecular weight acid or alkaline compounds will also gonna work for us, and maintain a neutral pH to minimize microbial activity, which is wrong because at neutral pH the microbial activity is more. And then fourth is utilizing both low and high pH extremes to inhibit microbial growth, which is also correct. So 1, 2, and 4 options are correct here. Okay, so let's discuss about drying. So which of the following statement is are correct regarding factors affecting the humidity accelerates the drying rate? Then air velocity plays a significant role in convective heat transfer during drying. And fourth is air velocity is more important when conduction and radiation heat transfer in all drying methods. Okay, let's discuss the solution, which is 1 and 3 options are correct here. So basically there are two terms, drying and dehydration. So drying is basically the removal of water to up to a desired level, whereas dehydration is that we are removing the water up to bone dry condition. So this is like more low water content. So drying is basically a complex process which is involving simultaneously the heat and mass transfer operations. So it is mainly physical in nature and can result in desirable and undesirable physical and biochemical changes. Also, it can, because of the heat and water removal, it can be there. Heat addition and water removal. So basically heat is going to supply to the food product. This is the food product. So heat is going to supply to the food product. Then the phase change in the food product is there, like from water. Water phase will going to convert from liquid phase water, which is from to the vapor phase, which is gases form. So this way, the mass transfer is going to be there. So there is a transfer of heat which provide the necessary latent heat of vaporization, and then there is a movement of water or water vapor through the food material and then away from it for the effective separation of water and the food. So first water will going to take up the energy and convert it into vapor, and then this way heat transfer is there. After that the mass transfer is there because water vapor is going to remove. So there are different kind of heat transfer modes: conduction, convection, and radiation. And when the water is removing from any food product, suppose this is a food product and water is removing from it. So first from A to B will going to happen. That means first the free moisture will going to remove, and after that there is a constant rate of drying we can obtain. This is a constant rate of drying. And after the free water is removed, the bound water will be there. So we can see the falling rate is there. So there will be two falling rates, first falling and second falling rates. So first uh, the bound water will like the water which is inside of the food will come out, and this is the water which is very close to the food particle. Okay, so yeah, so then first falling rate is there because the water which is very near to the food product, which is near to the food product or the inter in the first the intermolecular water will come out, and then which is very near to the food product or very in the very close bond to the food product. So it will need more heat energy so that to come out from the food material. So when the constant rate of the drying or the free water is removed, and it will convert to the falling rate or the bound water state. So this end C point is the critical moisture content. So this is the basically rate of drying. So this way the water will come out from any food product. Okay, so basically, as per if we discuss our question, what are different factors which are affecting the rate of drying? So the temperature is very important factor which is impacting the rate of drying. So if the temperature is increasing, the rate of drying is also increasing, and if the temperature is decreasing, rate of drying will gonna be decreased. Then relative humidity. If there is a decrease in the relative humidity, then there is an increase in drying rate. So there is a inverse relation between relative humidity and rate of drying. Then air speed and the velocity. So in convective heat transfer, air velocity is effective, whereas in the conduction and in the radiation heat transfer, so it is less important. This air speed is less important because air speed is more important in convective type of heat transfers. Then product composition. So basically it affects the effective moisture diffusivity. So if the product is more in the porous structure, so the diffusion will be faster, whereas if it's fat rich, so the diffusion rate of the moisture diffusion will be slower. Then product surface, so increase in the surface area will gonna have the positive effect on the drying rates, because more surface area, more heat will be there received and from the medium, and more amount of the moisture removal or the drying will be faster. And then characteristic dimension or the thickness of the product. So if the increase in the characteristic dimension or the length, the if the basically the product is more thick, then what will going to happen? The drying rate will be lesser. So increase the temperature, we're gonna increase the drying rate. It is correct. And air velocity will play a role in the convective heat transfer mode, and in conduction and radiation it is having So in conduction and convection, it is not having that much of high value. This, or less, it is less relevant, less important, this air velocity in the conductive and the radiative heat transfer. And if there is a high relative humidity, so that means more, I'm so sorry. Yeah, if there is a high relative humidity, then there will be low drying because it is inversely proportional. So second is incorrect. So 1 and 3 statement are correct here. Okay, let's solve this numerical question now. That the potato contains 95% moisture content on wet basis. How much will be its percentage moisture content in dry basis? So moisture content in dry basis is equals to basically mass of water divided by mass of the dry sample into 100. So we need to convert this moisture content from wet WB to dry basis DB. Okay, let's solve this question. So the moisture content in wet basis is 95%. So 95 divided by 100, it will be 0.95. Then moisture content in dry basis is equals to basically moisture content in wet basis divided by 1 minus moisture content in wet basis into 100. So here is that the dry basis of the moisture content is equals to wet basis upon 1 minus wet basis. If we are here, 100 is because we are converting into percentage, right? So dry basis is equals to wet basis moisture content is 0.95. So 0.95 divided by 1 minus 0.95. So 0.95 divided by 1 minus, so it will be 0.95 divided by 1 minus 0.95, which is 0.05, right? So it will be around 19. So if we convert into percentage, it will be into 100, which is 1900 percentage in percentage. Okay. So B is correct here, 1900. Okay. So let's move to this question, which is about blanching. So assertion is saying that the blanching is used as a pre-treatment method before freezing, drying, and canning. Reason is saying that it destroys enzyme activity in fruits and vegetables by heating them appropriately and using water, steam, or such systems. So we need to tell here which option is correct, like the which is true, assertion, and the reason, and if assertion is reason is correct, reason about the assertion or not. Okay, so here both assertion and reason are correct, and the reason is the correct explanation of assertion. So the basically here we are talking about blanching. In previous week 2 also we discussed about blanching. So blanching is basically a mild heat treatment that is going to inactivate the enzymes and it is going to destroy the microorganism that might contaminate raw vegetables and the fruits during production, harvesting, and transportation. So mild, this blanching and pasteurization, they are basically coming under mild heat treatment, whereas the canning baking, roasting, frying, they are the severe processes or severe heat treatment methods. So this blanching is basically is a pre-treatment which is used to improve the storage quality in the processes like freezing, drying, and canning. So before we are freezing or drying any food product or vegetables or canning, we use basically blanching as one of the pre-treatment methods, so that the microorganisms load will be come down, and also its main target is to deactivate the spoilage enzymes, and it prevent the spoilage and undesirable changes because it is deactivating the enzymes. So this blanching is done using steam and hot water blanching, and this is known as wet blanching because we sorry yeah. So when we are doing with the water or steam, this is known as wet blanching, and sometimes we do with hot air is blanching. So that is called hot air blanching. So when blanching is done using steam, so vegetables are exposed to the steam around 100 to 200 degrees Celsius for few seconds. And in hot water blanching, so the vegetables are kept in the boiling water for 1 to 3 minutes. And after that, immediate cooling will be there for the using the cold water. So advantage of the blanching is that it is inactivating the enzymes which is present into the tissues, and it stops enzyme actions that causes a loss of color and the flavor, and it shortens the drying and rehydration time. Whereas the disadvantage is that there is a loss of the nutrients when we are doing hot water blanching or the compared to the steam blanching. So in hot water blanching, more amount of the nutrition loss we can see. Then steam causes uneven blanching, so its efficiency is low, and higher investment is there in the steam blanching. So as we talked that the water and the steam if we are using, that is a wet blanching, and if it and this blanching is basically going to why we are doing this blanching as a pre-treatment method, because also it removes the air from the raw vegetables, and it reduces the chances of the corrosion. It prevents browning in certain products, and it softens the tissues and make it easier to fill, and it helps to preheat the product before sealing. So this hot water blanching is basically done when the clean food is subjected to the hot water, which is around 85 to 100 degrees Celsius, and it is done until the micro enzymes are inactivated, and port blanchers are used at the home scale. And its advantage is that there is a low capital cost and better energy efficiency, and but the disadvantage is that there is a loss of the water soluble substances, and if the water is contaminated, there is a higher risk of contamination of the food product, and there is a high effluent is produced uh, in hot water blanching. So in steam blanching, basically the food product is exposed to steam to avoid the loss of the food soluble solids. But its problem is that it is having a higher capital cost, and uneven blanching is there, and low efficiency and longer blanching time. And its advantage is that there is a low loss of water soluble substances, and less volume of the waste is generated, and it is easy to clean. So there are in this table, there are different vegetables like the peas, and its blanching temperature 85 to 90 and for 2 to 7 minutes. In carrots, around 90 degrees Celsius for 3 minutes. And in cauliflower, around 100 degrees Celsius for 2 minutes. So it is a like high temperature and low time method. So if we see here that the blanching assertion is correct, that it is used as a pre-treatment method for freezing, drying, and canning. And reason is also correct and explaining the assertion well, that it destroys enzyme activity, and heating them appropriately using the water, steam, or such systems. The next question is about which of the following statements is correct regarding the principle and methods of thermal processing. So thermal processing is mainly used to reduce or destroy microbial activity in the food. Then second is enzyme activity can be destroyed or reduced through thermal treatment. And third is thermal processing always leads to undesirable chemical changes in food. We need to tell which one is the correct statement. Okay, so here statement 1, 2, 3, all of them are correct. So this thermal basically processing, it basically reduces or destroys microbial activity, and then it also targets enzyme activity to improve the shelf life and stability, and it reduces or destroys enzyme activity, and then it does not always basically lead to the undesirable changes. Sometimes it causes the desirable changes like physical and chemical transformation are often indeed like the gelatinization and denaturation. So if this intended transformations like physical and chemical transformations are required, so thermal processing can be helpful. Then, as we already discussed, that the thermal processing can be mild, like blanching and pasteurization, and it can be severe, like the canning, baking, roasting, and frying. And it is basically categorized into categories. One is in container sterilization or the bulk canning, and the aseptic sterilization, which is aseptic processing and packaging. So here it is saying correct that the thermal processing is basically reducing and destroying microbial activity in the food, and it is reducing the enzyme activity, and also thermal processing basically always leads to undesirable chemical changes in the food. So basically, uh, sometimes basically it causes the desirable physical and chemical changes. So this statement is like 50% correct, and but it is saying that the chemical changes. So obviously it will lead to undesirable chemical changes because yeah, because of the thermal processing, there can be Maillard reaction, and the caramelization also can be there of the sugars. Uh, okay, let's move to the next question. So this is a numerical based question. In a food sample, the starting concentration of Clostridium botulinum was 10 to the power 8 CFU per ml. Following a 1.5-minute heat treatment at 121 degrees Celsius, this concentration decreased to 1 CFU per ml. So we need to find the D value of Clostridium botulinum at 121 degrees Celsius. So the starting concentration of Clostridium botulinum was 10 to the power 8 CFU per ml, and it decreased to 1, right? When we are giving 121 degrees Celsius for 1.5 minutes. We need to tell D value. Okay, let's see. So microbial count is initially higher, and then when we, with the time or with the heat treatment, the microbial population is coming down, uh, as we can see in the microbial survival curve. So the initial concentration is given as 10 to the power 8 CFU per ml, and the final concentration is 1 CFU per ml, and the treatment time is 1.5 minutes. And we need to find the value of Clostridium botulinum at 121 degrees Celsius. Right. So here, as we talked about, this is a microbial survival curve, and it follows first order equation, which is x equals to x naught e to the power minus kt. So here k is rate constant or the death rate constant. So x equals to x naught e to the power minus kt. So x is the final concentration of the microorganism, which is 1 CFU per ml, and equals to x naught, which is the initial concentration 10 to the power 8 CFU per ml. Then multiply e to the power minus k. So k is we need to find into t. T is 1.5 minutes. So 1.5. So when we solve this, it will be 1 by 10 to the power 8 equals to e to the power minus 1.5 k. Right. So when we take ln both sides, it will be ln 1 by 10 to the power 8 equals to minus 1.5 k. Right. So k will be ln 1 by 10 to the power 8 divided by minus 1.5. So this ln 1 divided by 10 to the power 8 can be written as ln 1 minus ln 10 to the power 8, right? So that will be, then k will be ln 1 minus ln 10 to the power 8 divided by minus 1.5. So when we solve this, we will gonna get k value as 12.28 per minute. Please try to solve and let me know if you're getting the same value. Right, we get from here that what is the value of k from because we know that the microbial survival curve from the that it is following a first order reaction. So we just put and we just get to know what is k or the k, which is the death rate constant or the rate constant value. Now we need to calculate d value. What is d value? Which is decimal reduction time. So it is basically the time required to destroy 90% of the organism. D value is numerically, it is equal to the number of minutes required for the survival curve to traverse one lobe cycle. So mathematically, it is equals to reciprocal of the slope of the survival curve, and it is the measure of the death rate of a microorganism. So when we plot this survival curve in the logarithm scale, so this is a semi-log curve. So this is in the log, and this is normally. So that is a semi-log curve. So one log cycle when it is reducing. So how much is the this time is required? That is d value. So d value equation is d equals to 2.303 divided by k, which is the here this value k log x by x naught. So x is basically the initial population, and x naught is basically x naught is basically the initial population, and x is final population. So as we are saying that the D value, this X, basically X to X naught, if we talk about. So X value is basically what amount of the population, microbial population we get after transversing the one log cycle. So that is basically that tells that the X is equals to 0.1 of the X naught. So when we keep here, so it will be log X. X is basically 0.1 of the X naught, or 10% reduction in the microbial population, right? Divide by X naught. So it's 0.1. Here it is saying 90% of the population will kill and only the 10% of the population will be survive. So X naught is the initial population, and finally it's only 10% population will survive, which is 0.1 of X naught. So when we solve this, it will be log 0.1. Which is equals to 1. So the D value will be 2.3. This will be equals to 1. So D will be 2.303 by K. So K we got from here. So we can write D equals to 2.303 divided by K, which is 12.28. So D value will be 0.1875 minute or 11.25 seconds. So which is around this option, first one. Okay, let's solve next question about Z value. If an increase in the process temperature from 100 to, so if we are increasing from 100 to 110 process temperature, it reduces the D value from 5 minute to 0.5 minute. So we need to calculate Z value now. Okay, let's solve this question. So if there is an increase in the process temperature, so that means the D value will going to come down, and Z value we need to calculate here. So Z value is basically the thermal resistance constant, and it is basically the temperature value, which is in degree Celsius. So it is basically the slope of thermal death time curve, TDT curve, which is this curve. This is basically the curve in which in x-axis there is temperature, and in y-axis D value, decimal reduction time value is there. So the number of degrees required to bring about tenfold change in the decimal reduction time is the Z value. So if there is a tenfold reduction in the D value, like from here to suppose here, so we'll take this in this curve, and this from this slope we will calculate what is the temperature is there. So that temperature is Z value. So the temperature increase for a one log cycle change in the D value is Z value. So Z is T2 minus T1 divided by log D1 minus log D2. So T2 is temperature 2. So at temperature 2 minus temperature 1 divided by log D decimal D value, which is decimal reduction time value D1 minus log D2. So we, according to the given data, initial temperature is 100 and it is increased from 100 to 110, and D value is 5 minute to 0.5 minutes. So Z value is equals to T2 minus T1 upon log Z1 log D1 minus log D2. So we just need to put values. So T2 is 110 minus T1, which is 100, divided by log D1, which is log 5 minus log D2, which is log 0.5. So when we solve this, it will be 110 minus 100 is 10 divided by log 5 is this 0.698 and log 0.5 is minus 0.301. So minus minus will be plus. So 10 divided by 0.698 plus 0.301. And when we add this denominator, it will be 0.999. So 10 divided by 0.999 will be 10 degree Celsius. So Z value will be option A, 10 degree Celsius. Let's solve next question, which is a canning process is conducted at 121 degrees Celsius and the thermal resistance value, which is D value of Clostridium botulinum spores at 121 degrees Celsius is 0.21 minutes. The process needs to achieve a 12 log reduction of C botulinum spores to ensure safety. So we need to calculate here the F value in minutes for this process. Okay. So what is first F value? So F value is thermal death time. So it is a total time required to accomplish a stated reduction in a population of vegetative cells or spores. So this time can be expressed as a multiple of D value as long as the survival curve follows the first order model. So suppose we are saying that 99.99% reduction in the microbial population would be there. So it will be equivalent to 4 log cycle reduction, or F equals to 4D. A typical thermal death time in thermal processing of stable shelf-stable food will be F equals to 12D, with the D value is for the Clostridium botulinum. So now let's see the question. That in the question we have given data is that the D value of the Clostridium botulinum spores at 121 degree Celsius is 0.21 minutes, and there is a log reduction of 12 times 12 log reduction of C botulinum spores. So F will be D into log n by n naught. So F equals to D value, which is 0.21, and log n by n naught, which is the 12, which is how much is the log reduction? 12 log reduction is there. So when we multiply 0.21 into 12, it will be 2.52 minutes, which is the F value here. Okay, let's solve this question, which is about evaporator, single effect evaporator. So apple juice is being concentrated. Basically, this apple juice is there, which is fed into this evaporator. So apple juice is being concentrated in a natural circulation single effect evaporator at a steady state condition. Then basically this apple juice is given in this evaporator to concentrate. So this one side this dilute apple juice will come, and this side the steam will come in this evaporator system. So the concentrated product will come out, and the steam will see from in the like after the exchanging of the heat, the steam will come from here in the form of basically the steam will convert into liquid and it will come out, and then the vapors from the product, the dilute product is converted into the concentrated one, right? So the vapor will come out. So apple juice is basically being concentrated in a natural circulation single effect evaporator. So at steady state condition, this dilute juice is the feed introduced at the rate of 0.67 kg per second. So this is coming at 0.67 kg per second. The concentration of the dilute juice is basically 11%. Solids is there in this dilute juice, total solids. So the juice is concentrated basically to 75% of the total solids. The specific heat of this dilute apple juice, and the concentrated apple juice is given as 3.9 and 2.3 kilojoule per kg degree Celsius respectively. And the steam pressure is given as 304.42 kilopascal. The inlet feed temperature is given as 43.3 degrees Celsius, and the product inside the evaporator is at 62.2 degrees Celsius, and the overall heat transfer coefficient is given as 943 watt per meter square degree Celsius. And there is a, as we need to assume that the negligible boiling point elevation is there, and we need to calculate the mass flow rate of the concentrated product, the steam requirements, steam economy, and the heat transfer area. Okay, let's solve this question. So in this question, we have given the mass flow rate of the feed, which is 0.67 kg per second. Then the concentration of the the total solids in the feed stream is 11%. So we can write it as 11 by 100 is 0.11. Then concentration of the the two solids in the product is, or the final concentrated juice is 75%. So 75 divided by 100 is 0.75. And then steam pressure is 304.42 kilopascal. And then feed temperature is 43.3 degrees Celsius, and the boiling temperature T1 in evaporator is 62.2 degrees Celsius. And the overall heat transfer coefficient is U is given as 943 watt per meter square Kelvin. And then the specific heat of the diluted feed is given as, in the question, as 3.9 kilojoule per kg degree Celsius. And the specific heat of the concentrated product is basically 2.3 kilojoule per kg degree Celsius. So all this question is basically based on the overall the mass, the balance of the mass and the heat transfers balances will be there in this question. So first we need to calculate here the mass flow rate of the concentrated product, which is MP. We need to calculate first. So the mass flow rate of the dilute feed into its uh, which is MF. So mass flow rate of the dilute feed into its solid fraction in the feed, which is XF. So is equals to XP into MP. So XP is solid fraction in the product stream and into its mass flow rate of this concentrated juice, or the finally the product we get is a concentrate product. So that is equal. So XF is given as 0.11 into 0.67, which is mass flow rate of the feed. So 0.11 into 0.67 is equals to basically XP, which is the concentration in the product. So total solids are 75% or 0.75 into MP, which is the mass flow rate in the of the product, or the concentrated product, concentrated juice. So that is MP. So that we need to calculate. So MP would be 0.11 into 0.67 divided by 0.75. So that, so MP, which is the mass flow rate of the concentrated product, will be 0.0983 kg per second. So based on the mass flow, we can say that the mass flow rate of the feed stream is equals to what is the concentrated we get and what is the vapor we go out, is equals to mass flow rate of this concentrate plus this vapor which is going out. So MF is equals to MV plus MT, where this MV is mass flow rate of the vapor in kg per second. So this MV will be going to equal to the MF minus this MP. So it is equals to MF, which is given in the question as 0.67, minus MP, which we calculated at 0.0983, so which is equals to 0.5717 kg per second. Now we can calculate, and this is basically the mass flow rate of the vapor. This is mass flow rate of the product we got right now, concentrated product. Then now we need to do the enthalpy balance. So we're gonna calculate the different enthalpies of the different fractions. So basically, this is the enthalpy balance which is in the evaporator system overall, which is involving the enthalpy of the feed, this one, and it multiplied by its flow rate. So MF into its enthalpy, HF, plus this steam. So MS, which is its flow rate, into its enthalpy, is equals to the enthalpy of this concentrated product fraction, which is concentrated juice, which is MP, its mass flow rate, into its enthalpy, which is H of HP, and then plus of this steam, which is after exchanging the heat, which is MS, into its enthalpy, and then plus this vapor enthalpy into its mass flow rate. This is the overall mass flow rate. So to calculate this, we need to have different terms. So we'll calculate different enthalpies first, and then we'll put in the this mass flow rate equation. So here in this equation, MF is, we know, mass flow rate of the feed. Then HF is enthalpy of the dilute liquid feed. And then MS is mass flow rate of the steam, into HV is basically the enthalpy of the saturated vapor, is equals to MV, which is the mass flow rate of the vapor, into HV1, which is enthalpy of this saturated vapor at temperature T1, plus MP, which is the mass flow rate of the concentrated product, and into its enthalpy HP1, which is enthalpy of the concentrated product, plus MS, which is mass flow rate of the steam, into its enthalpy, which is enthalpy of the condensate, enthalpy of this condensate. Here, TS is basically the temperature of the steam, and T1 is the boiling temperature maintained inside the evaporator, and TF is the temperature of the feed in this equation. Okay, so in this equation, we have this MF, which is enthalpy of the feed. Sorry, mass flow rate of the feed, which is given in the question already as 0.67. Right? So 0.67 here, but we don't know its enthalpy. So we need to calculate its enthalpy term, which is HF. So how we going to calculate this HF, which is enthalpy content of the feed, which is equals to Cp into delta T, right? So HF is equals to Cp, which is a specific heat of the feed, is given in the question as this one, 3.9 kilojoule per kg degree Celsius. So 3.9 kilojoule per kg degree Celsius into its temperature. So the product temperature is given in the question, the feed temperature is given in the question as 43.3. So we'll multiply 43.3 into 3.9. So it will be 168.87 kilojoule per kg. So here we'll put 168.87 kilojoule per kg, then plus MS, which is mass flow rate of the steam, which we need to calculate, into its enthalpy, which we will going to calculate from one table. So we need to calculate the mass, this HVS, which is basically the enthalpy of saturated vapor at the temperature of the steam. So in the question, the steam pressure is given as that the steam is at a pressure of 304.42 kilopascal. So from the steam table, we can say 304 I'm sorry, this one. 300, this in between this, right? So 304.4 kilopascal will come somewhere in this. From interpolation, we can say that at this temperature, this pressure of the steam, 134 is the temperature from the table, right? This table. So it will come somewhere between 130 to 135 because of the pressure we already know. So 134 is the degrees, 134 is the temperature of the steam, right? So at this temperature, what is the enthalpy of the saturated vapor? So it will be somewhere between in this, we need to calculate by interpolation. So it will be at 134 degrees Celsius, the saturated vapor pressure enthalpy is 2725.9. So this steam saturation vapor pressure is 2725.9, then is equals to mass flow rate of the vapor stream, which is MV. So MV we calculate already this one 0.5717. So we calculated, put here into its HV1, which is its vapor pressure, right? So how we can get it? We can get this also by from the table. So what is happening from when the steam is going at 134 degrees Celsius here, the vapor, this is feed is going, dilute juice is going, and the steam is going at 134 degrees Celsius. Then in the evaporator, the concentrated product is coming out and the vapor is coming out, and also this steam, how it is it is converted, this steam in the form of the liquid, which is water, and at the same temperature, which is 134 to 134 degree Celsius. So only there is the exchange of the latent heat here of the steam. So this HV1 is enthalpy of the liquid at temperature 134. So this is enthalpy of the saturated liquid here, not vapor, at 134 degrees Celsius. So we can get it from the table. This interpolation we can get from this. So what will you get? We will get 563.41 kilojoule per kg, and then enthalpy, then we can put it here. I'm so sorry. We have done, I think, some mistake. Yeah, so we were telling that here, we were here that HVS we calculated 2725.9, right? So we calculated based on this interpolation that 134 at 134 degrees Celsius, this is the basically value. Then MV, which is this MV is the mass flow rate of the vapor which is coming out from above. MV, I'm so sorry, I thought this is MS. So yeah, so this is MV. MV is basically this is the MV, mass flow rate of the vapor which is coming out, 0.5717, right? This one. So, and we need to now multiply by its enthalpy. So we need to measure the enthalpy of the saturated vapor at temperature T1 now. Temperature T1 is basically 62.2 degrees Celsius, means whatever the steam which will come out from the product, the vapor which is coming out from the concentrated product it will be at the same temperature which is inside the evaporator, and also the concentrated juice will also come out the same temperature. So the feed which is going inside the evaporator, uh, the feed is going and the vapor is coming out, and also the concentrated juice. So in the evaporator, it's 62.2 degrees Celsius. So both of these will come out at 62.2 degrees Celsius. And whereas the steam, which is at temperature 134 degrees Celsius, how we get to know from this pressure? Because at this pressure of the steam, 304.42 kilopascal pressure of the steam, 134 degrees Celsius temperature is there, which is calculated based on the table of the steam. So this steam will basically give its latent energy to this to make the product concentrate, and the liquid will come out, which is at 134 degrees Celsius will come out of this steam. So since we are talking here about MV, MV is basically for the vapor which is coming out from the concentrated product after getting the concentrated product. So which is at 60, the temperature of it is 62.2 degrees Celsius. So based on this table, 62.2 degrees Celsius, this one, it is somewhere between here, right? The vapor will be somewhere between here. So that's based on the interpolation, we can get at 62.2 degrees Celsius temperature, the enthalpy of saturated vapor HV1 is 2613.4 kilojoule per kg, which is this, plus the product, concentrated product mass flow rate, which is 0.0983 into its enthalpy, which is, here we calculated the enthalpy of the product, concentrated product is equals to its specific heat into temperature. So its specific heat is given in the question as 2.3 kilojoule per kg degree Celsius, which is multiplied by its temperature, which is in the inside evaporator, it gets the temperature around 62.2 degrees Celsius. So 62.2 into 2.3 is equals to 143.06 kilojoule per kg. So 143.06 kilojoule per kg here, plus this is basically the liquid after heating. So MS is a mass flow rate of the steam. It will be same because the mass flow rate of the steam will be same into its enthalpy. So the enthalpy is now at 134 degrees Celsius. What is the enthalpy of the liquid, saturated liquid enthalpy? It will be based on the table between 546 to 567. So it is around 563.41, which is this 563.41. So when we solve this, so it will be 0.67 into 168.87 will be 113.143. Then MS into 2725.9 equals to 0.5717 into 2613.4, which is equals to 1494.08 plus 0.0983 into 143.06, which is this 14.06 into plus 563.41 into MS. So now MS, this is MS term and this is MS term. So it will come here. So 2725.9 minus 563.41, which is 2162.49 MS. And 14, and on right hand side 1494.08 plus 14.06 minus 113.143 is equals to 1394.997. So MS will be this 1394.997 divided by 2162.49. So it would be equals to this 0.64 kg per second. So this is the mass flow rate of the steam. Now the steam economy we need to calculate, which is the basically ratio of the rate of the mass of water vapor produced from the liquid feed per unit rate of the steam consumed. So steam, how much is the consumed? So MV is basically 0.57 divided by MS. MS is basically 0.67, which is equals to 0.85 kg water evaporated per kg of the steam. So next is we need to calculate the area. Here area, heat transfer area. Yeah, we need to calculate heat transfer area. So area is Q equals to UA. Q means that is rate of heat transfer is equals to overall heat transfer coefficient into its area into delta T. So which is equals to MS, because heat is exchanging using the steam. So M is its mass flow rate into the enthalpy exchange from Vs, which is the saturated steam, from to when the concentrated liquid we are getting, so it will be coming into the saturated liquid at the same temperature. So only the latent heat is transferred, right? So area A into the overall heat transfer coefficient, which is 943 given in the question, and multiply by what is the temperature change. Temperature is changing 134 steam and minus 62.2, which is the evaporator temperature inside, equals to MS, which is given like we calculated MS as from here 0.64 kg per second, multiply the subtraction of the enthalpies, right? When the steam, saturated steam enthalpy minus at 134 degrees Celsius minus the enthalpy of the saturated liquid at 134. So that is 2725.9 minus 563.41. This one. So area into 943 multiply 134 minus 62.2 would be area into 707.4 equals to, on right side it would be 0.64 multiplied by 2725 minus 9, 2725.9 minus 563.14, which would be equals to 1384.1664 multiplied by we are converting 1000 joule per kg, that is we are converting into joule, so it would be around 1384.1664 into 1000 divide by 67 707.4. So it would be 20.44 meter square. This area would be 20.44 meter square. And here, if we see, this is basically watt per meter square. So I missed here unit. So this is basically watt per meter square. Okay, so let's move to the next question now, which is about the preservation by removal of heat, which is basically the chilling or freezing. So chilling is basically done at -1 to 8 degrees Celsius so that the sensible heat or the field heat can be removed, and the heat generated due to the respiratory activity can also be removed. Okay, so a storage facility manager is setting up temperature controlled rooms to store various fruits. So the facility includes tropical fruits such as the mango and the banana, and the subtropical fruits also like the citrus fruits and the avocado. The manager plans to store all these fruits at 5 degrees Celsius to extend the shelf life. Based on the chilling injury susceptibility of the tropical and subtropical fruits, which of the following statement is correct? The first statement is storing tropical fruits below 12 degrees Celsius is not advisable. Then second is subtropical fruits are sensitive to temperatures below 5 to 8 degrees Celsius. Third is that the fruits grown in temperate regions are more susceptible to chilling injury than the tropical fruits. And fourth is all fruits in the facility can be safely stored at 5 degrees Celsius without risk of chilling injury. So we discussed about chilling injury in a detail in previous lecture already. So here answer is 1 and 2, that storing tropical fruits below 12 degrees is not advisable, and subtropical fruits are sensitive below 5 to 8 degrees Celsius. So the chilling injury can be observed in basically fruits and vegetables like peaches, bananas, mango, zucchini, etc. at the low temperature and when it is stored for some time. And it is basically a physiological defect in the plants and the products that results in the reduction in the quality and loss of the product utilization following exposure to low but non-freezing temperatures. Symptoms may include pitting, browning, softening, and even the decay. And these negative effects will reduce the consumer's desire to buy the fruits and vegetables, resulting in a large amount of the economic losses. These symptoms basically appear at the room temperature after after the product is removed from the refrigeration. So the so for the cold sensitive temperature for the subtropical fruits, it is around 5 to 8 degrees Celsius, while for the tropical fruits, it's maybe less than 12 degrees Celsius. Temperate fruits, they are less sensitive to chilling than the tropical or the subtropical fruits. 5 degrees Celsius can cause basically chilling injury in both the tropical and subtropical fruits. So the basically the biochemical mechanism behind chilling injury is cell membrane damage hypothesis and reactive oxygen stress hypothesis. So these two hypotheses, they tell that the cell membrane function is disrupted. That's why the physiological metabolic disorders can be observed. Like this is the mechanism that the liquid crystal in liquid crystal state, this membrane is there. The membrane lipids, they are in the liquid crystalline state, but because of chilling injury, it is converted into solid gel. So because of that, there can be the increase in the cell membrane permeability and the electrolyte leakage, and thereby the cell damage and the cell lysis. Also, because of the changing of this lipid membrane into the solid gel, the function of the membrane proteins, they are disrupted, and the photosynthesis and the respiration rate will go down, and the more of the reactive oxygen species will form, and because of that, the cell membrane oxidation can be seen. Also, the fatty acid peroxidation can be seen, and therefore the cell is damaged and lysis. Also, the third is that the Ca2 plus cytosolic amount is increased, and the fatty acids will be more, and they will be oxidized, peroxidized, and overall the cell will be damaged or lysis. Yeah, so in the kiwi fruit, if we see the chilling injury, uh, so this is a kiwi fruit. So the surface water stains we can see here in this picture. So because of the chilling injury, there is surface water stains. Then in the guava, there is a loss of the ability to mature the fruits. And then in banana, we can see there is a surface depression and also the browning due to the chilling injury. And in this, it is basically peach. So in the peach, there is a woolly texture is there. And in this bell pepper, the seeds and the calyx, they are getting brown. You can see here, browning. So this is all the symptoms of the chilling injury in different fruits and vegetables. Okay, let's discuss this next question that the assertion is given that aseptic processing involves basically the sterilization, the product and the packaging material separately and then packaging in the aseptic environment. And reason is saying that very high temperature like 200 to 300 degrees Celsius are generally used in aseptic sterilization of the product, commonly referred to as UHT or ultra high temperature process. So we need to tell here whether the assertion and the reasons are true or false, and if the reason is correctly or not correctly explaining the assertion. Okay, so here if we see uh, assertion is basically true, but the reason is basically false. So in aseptic processing, basically, the product is basically subjected to a thermal process to inactivate the vegetative cells or the spores prior to being placed in a sterilized container. So the product is basically uh, sterilized differently and the package is differently sterilized and then they'll put in the sterilized atmosphere. So the product and the container or the package are sterilized separately and then put them together in the sterilized environment to using a form, fill and seal machine. So here the food is basically sterilized and it will come and then package is sterilized and come in this aseptic condition, sterilized condition, and then the fill and product we can get. So this is done basically to create a safe, ready to eat, self-stable product that can be transported usually without the refrigeration. Since very high temperature is there, typically 130 to 180 degrees Celsius in aseptic commercial sterilization, these processes are generally referred to as a UHT, ultra high temperature processes. So the process are basically based on the enzyme inactivation, since some enzymes exhibit greater heat resistance in the temperature ranges than do the microorganisms. So heat exchange equipments which can be used is scrap surface, plate heat, tubular, and steam injection based. So if we see UHT process of the milk, it takes around 1 to 8 seconds of heating at 135 to 154 degrees Celsius. And because of the UHT process, some kind of undesirable changes can occur like deterioration of color, flavor, and texture as observed in phenomena like the cooked taste in the UHT milk or loss of the chlorophylls and the texture problem in the canned and dehydrated vegetables and toughening of the muscles in the frozen fish and seafood. So these are the different fruits on like the basically fruit juices and the nectar. So about their UHT processing condition and how they control the microorganism count. UHT, it is can be used for fruit juices, honey, wine, cream, soya milk, yogurts, soups, and stews. So, like if we talk about the carrot juice, at 110 degrees Celsius for 8.6 seconds, this is done to reduce the plate count to 4.9 log and the yeast and mold to non-detected level. So here reason because it is saying that 200 to 300 degrees Celsius. So it is wrong because in UHT we don't go this high temperature. Okay, let's discuss this question about radiation. So we identify which of the following statement are true or false regarding type of the radiation used in food processing, and accordingly choose the correct option. So gamma rays and the X-rays are classified as ionizing radiation. Alpha particles and neutrons are examples of electromagnetic radiations, and electrons and protons are the type of the particulate radiations, and X-ray are a form of the particulate radiations. So which statement is true, false? Please let me know. Okay, so answer A is correct, that statement 1 is true, then second is false, then third is true, and fourth is again false. So basically radiation is the emission or the transmission of energy, basically in the form of the waves, or sometimes in the form of the particles, through space or a material medium. So photons, electrons, protons, ions, neutrons, and so on, which have the energy, are basically considered as radiations, whereas irradiation is basically the process of exposing a fluid or the model to that radiation. So suppose this is a molecule or atom in which radiation is applied. So the electron is knocked off. So high energy proton is coming, knocking off the electron from its orbital, and the proton with reduced energy is going on the other side. So this electromagnetic radiation, so these are radiation are considered in electromagnetic radiation and the particulate radiation. So the electromagnetic radiation, they are the consisting of the photons that have the energy but no mass or charge, such as the radio wave, microwave, infrared, visible light, ultraviolet, X-ray, and gamma rays. A photon basically is described as by the quantum theory as a particle or the quantum that contains a discrete quantity of electromagnetic energy which travels at a very high speed, like a speed of light. So these are the electromagnetic radiations. So this is electromagnetic spectra. So all these radio wave, microwave, infrared, visible, ultraviolet, X-rays, and gamma rays, they are in the electromagnetic spectrum. Then the particulate radiation are there. So they consist of basically the particles that have the mass and energy, and may or may not have an electric charge, such as the alpha radiation, beta radiation, proton radiation, neutron radiation. So particulate radiation contains basically electrons, protons, neutron, and alpha particles. So basically, like this is the nucleus of atom. So from this, high energy electrons can be emitted. So that is basically beta radiation, and then high energy electromagnetic photons are emitted, which is gamma radiation, and then uh, basically the alpha radiations are the one where two protons and two neutrons are there. So this kind of from the nucleus, this radioactive decay is there, and there this kind of particulate radiation are coming out. So the gamma and X-rays basically are the ionizing radiations. Alpha particles and neutrons, they are particulate and they are not the electromagnetic. Then electrons and protons are particulate radiations, and X-ray are not particulate, they are the electromagnetic radiations. So here only 1 and 3 statement are correct and 2 and 4 are false. Okay, let's discuss the last question of today's class that match the column 1, which is having different type of food irradiation methods, and in column 2 we have the corresponding purpose or the dose. So we need to match here in this question. Okay, let's see the answer. So D is correct. Basically, food irradiation basically is exposing the food to the controlled energy or ionizing radiation. So gamma rays, they are produced normally from 60 cobalt source, and X-rays with the energy up to 5 MeV, which is or sometimes up to the 10 or the electrons up to the 10 MeV electron volt. So it basically kills microorganisms without raising the food temperature. this irradiation. So this irradiation technology can be like adaptation, which is basically very high dose, and basically it is the sterile for the sterilization purpose. So it is up to 4.5 mRAD. So RAD is basically in this much, this unit mRAD is basically the unit of the this much of the radiation is produced. That kills basically the all the bacteria and the viruses, and especially the Clostridium botulinum spores, because it is for the sterilization purpose. And then is the radiation, which is medium dose, 100 to 1000 kilo radiation to basically inhibit vegetable sproutings and the fruit ripening and the insect sterilization and kill around 90% of the organism. So it is kind of a pasteurization method. Then then radicidation, which is a low dose method, which is around 400 to 600 kilorad, and then that kills basically most of the pathogens and the spoilage organisms and the insects and the parasites. And it is also a pasteurization method. So this basically when there is a irradiation of any food, this kind of symbol we can see on the food product. So it can basically do sprout inhibition, insects disinfection, and then extension of the shelf life of the food products, then pathogen removal, and they'll help to quarantine the fruits, basically to increase the shelf life of the fruits. So basically this radioactivation is basically very high dose. So radioactivation is basically the medium dose, and radicidization is basically kill most of the pathogens, food products, and insects and the parasites, and it is of the low dose. Okay, so today we basically discussed how we can process the food products and preserve the food products. So we basically discussed what are the different principles and methods of preservation and processing, and what are the different factors which are affecting the growth of the microorganisms. Then we discussed about many factors like pH, water activity, redox potential, and we discussed also about the different composition of the food products, or any biological structure is there in the food product, or antimicrobial agents are there or not. Like that, we discussed about temperature, oxygen, stress also we discussed. Based on that, the different microorganisms, and then we discussed about the when we are removing the water in the by processing. So yeah. So yeah, we discussed about when we are removing the water. We are drying. So we also discussed about the calculations of drying and the evaporate, like the single effect evaporator. We discussed all the calculation about drying rate. Also we discussed, and then we discussed about the thermal process calculation, D values, add value, add value. We discussed, and we discussed about the blanching process, and then we discussed about the chilling injury, and then we discussed about the irradiation of the food. Uh, we discussed about the different techniques of the irradiation, and then in the next class we'll be discussing about cleaning and washing, and then sorting and grading, peeling, pouring and slicing, and uh, peeling, pouring and slicing, and then containers and packaging materials for fresh produce, and the packaging methods and equipments. We'll be discussing all these in the next class. So the recorded video of this class will be provided on the YouTube link, and the PDF or the PPT will be provided on this Google Drive link. Please feel free to ask questions or your doubts either in the live interaction session or in the Q&A. You can put your doubts on Q&A. So please, thank you so much. Please join the session. attendance is important. And thank you so much for joining the class. And this is the end of the session. So next class will be on next Sunday, 4 to yeah, so thank you so much for joining the class. I hope to see you all in the next session on Sunday, 4 to 6. So, okay.